And now we come to the most famous and useful test of them all. It's going to help us for the rest of the chapter on power series as we develop our own series. It's called the ratio test for absolute convergence, and what it does is you take this limit of the terms of the series, the terms of themselves, not some other series, but that series itself, and you create that limit and you watch where it goes. And the thing is, if it's less than 1, you have convergence. If it's greater than 1, it's divergent. If it's equal to 1, try another test. But not only does it converge with this test, it actually converges absolutely. The proof, well, the proof starts off something like this. If you were to take the limb, let's say that the limb, if we do a quick look at the proof of this thing, the limb as n goes to infinity, absolute value, an, what does he do? Plus 1 over an. He puts the n plus first term on top of the nth term. And let's say we get some sort of limit. Now, there are different cases, as you can see here. Let's do the case where it converges and we get less than 1. Okay. The way this goes, I am only going over this because it's pretty interesting how this is done in the book. You got a number line, right? And your limit L is here, let's say. And out here somewhere is the number 1. Okay, so the game is, they place some guy named R, if I get the right color that is. There we go. Places this guy named R between L and 1 because L is less than 1. Then they do this argument where if you go out far enough in the sequence of terms, you'll have this, since this is its limit, an plus 1 over an, then all these an plus 1 over an's are going to be within a neighborhood of this actual limit, and they're all going to be eventually, some of them at the beginning are way out there, but eventually they're going to be less than r. So we force it, okay, we're going to say it's going to be less than r, which is less than 1, right? Well, that means that absolute an plus 1 is less than r times, well, I'll write it this way. Yeah, I'll write it this way. R times absolute an. Okay, go to the next ratio, absolute an plus 2 over an plus 1. That's the very next ratio as they go down the line. You're creating the ratio of one term divided by the term ahead of it. And that's what this is saying in the ratio test. Well, that's less than, it's less than r also. So absolute an plus 2 is less than r times absolute an plus 1. But guess what? He's less than r times r absolute an. And what's developing here is the absolute an plus 2 is less than absolute an times r squared. So you've got this guy, you got this guy, there's a pattern, absolute an plus 3 maybe, less than absolute an times r cubed. And you know what? Here's the story. Story is this. This r is less than 1, and this is a geometric series. So that means it converges because r is less than 1. Okay? So that means these guys, where are you? Here they are. These guys are, a series. If you were to add them up, these guys also are. So it looks something like this. Series absolute an plus 1, n is equal to 1 to infinity or whatever, also converges. In fact, since they're absolute value, it converges absolutely. It's a real quick look at it. You can turn it around and have the limit greater than 1 and prove divergence the same way. It's really powerful and it's super easy to work with. And you know what else? It's really great for when you see powers and exponentials, as you see in these two examples we're going to do. These are the two examples I'm going to do with the ratio test. There's a root test here that's really quick, and that'll be the end of this guy. You can ignore the proof of that, but it's kind of interesting to note that if the limit of those ratios is less than 1, it's convergent. That's really interesting. it shows that, again, the terms are going to zero rather rapidly, and they gain convergence. This is not a good test for the problems that I showed you with the limit comparison test. Those are good for the rational functions. Whenever I run a ratio test on something like this, like 3n squared plus 2n all over n squared plus 2n plus 1, if I run it on this one, the ratio test always gets me 1. Back up here, this is what's important, because what we're doing with this test is we are running a ratio, and when you do the root test, you run the roots of the terms, and these conditions here are what tell you the answer to the problem. So let's do one. So I'm looking at series n is 1 to infinity. We've got minus 3 to the n all over 2n plus 1 factorial. Oh, I got to tell you, factorials start playing a big role in our homework, so watch out. If we run the ratio test, it goes like this. Okay, lim, n goes to infinity, absolute value, and what we do is we go an plus 1 divided by an. It's a ratio. So for us, it's looking like lim, n goes to infinity, absolute value. The an plus first term is this. It's minus 3 n plus 1 over 2n, whoops, let me do that right, 2 times n, but in this case, 2 times n plus 1 factorial. He is divided by the nth term, which is minus 3 to the n over 2n plus 1 factorial. Okay, it's similar to the limit comparison test. Those are two very popular good tests for convergence. Watch what happens. So we keep going. My worry right now as I'm talking this to you is I wonder if they're going to understand how the factorials cancel. I want you to be thinking of that as we go. And also, when we are doing absolute values, what happens to the negative 3? The negative on the 3, okay? So n plus 1 here. I'm going to invert and multiply next. This is 2n plus 3 factorial. And then invert and multiply 2n plus 1 factorial all over minus 3 to the n, okay? One thing's going to happen right away. I really don't care about the negatives inside the absolute value. In fact, you could just make them both positive because the terms are all turned positive. All right, and then the second part is how things cancel. So lim, n goes to infinity, absolute value. This is the fun part with the ratio test. You get to cancel stuff. So 3 to the n cancels with 3 to the n plus 1. This guy has 1 extra. So far our survivor is 3. How about those factorials? What about those factorials? One way to do it, I don't know if you're going to follow this, I hope you do, is 2n plus 3 times 2n plus 2, and then times 2n plus 1 factorial is what 2n plus 3 factorial can be written. And over here, we have 2n plus 1 factorial. Oh boy, that's a weird one. You notice, here's the thing I see. I see that plus 3 and plus 1 means the guy downstairs is 2 more than. So for instance, if I had 5 factorial divided by 7 factorial, well, mechanically it goes 5 times 4 times 3 times 2 times 1 all over 7 times 6 times, guessed it, 5, 4, 3, 2, 1. So really you can write it as 5 factorial all over 7 times 6 times 5 factorial, and the best part, cancel those factorials. And I'm going to cancel these factorials here, and we're well on our way. So we've got lim as n goes to infinity, absolute value, and all we have here, I'm going to write this a weird way. I'm going to write 3 times 1 over 2n plus 3 times 2n plus 2. You might pause and go, how did he do those factorials? But right now we're at the stage we take the limit finally. When we take the limit, the 3 just is along for the ride. What happens in this case is this guy right there goes to 0, doesn't it? So we end up with a limit that says 3 times 0 is 0, or you could have left the 3 upstairs and said it just goes to 0. So what's the big deal? The limit is 0. What do we draw? What kind of conclusion do we draw here? Well, back up here, remember, if the limit is less than 1, which it is, this means that the series converges. So we'll tell the world minus 3 to the n over 2n plus 1 factorial converges. You know what else? Absolutely, because that's what this test does for us. It either shows you it converges absolutely, which means it converges, or it shows that it diverges. There's an example of the ratio test. Let's do another one. So we have n factorial over 100 to the n. Okay, looks like we might want to squeeze it in here, maybe. So series, I think I saw n factorial on top of 100 to the n. Is that right? Let me check. Yep. Here's the thing. I know this author probably put this in to show, oh, 100 to the nth power is just going to grow like crazy. We're going to find out that n factorial is actually faster to infinity. Okay, and let's do it this way. So because of the factorials and the powers, it's a good idea to run the ratio test. So we will. So we run the ratio test. Which means we take the lim as n goes to infinity, absolute value, n plus first term, n plus 1 factorial, always goes on top. Who goes on top this time is important. The later term goes on top of the former term. So 100n plus 1, and we're going to divide by the nth term like so. And what I typically do is I skip that step and I just go invert and multiply. So we're looking at n going to infinity absolute value. Notice the absolute value here, n plus 1 factorial all over 100 to the n plus 1, invert and multiply times 100 to the n over n factorial. Well, once again, we'll check out on that factorial what's happening. We have lim as n goes to infinity. Okay, really n plus 1 factorial is n plus 1 times n factorial. And I'll just rewrite the rest, and then we get to cancel stuff. The ratio test is great because the powers cancel, the factorials cancel. No other test does that for us. So we're going to get our conclusion here shortly. You ready? Well, the n factorials cancel. All the n factors of 100 except 1 cancel downstairs, and we're getting lim as n goes to infinity, absolute value, n plus 1 over 100. What happens this time? N goes to infinity. He's in the numerator this time. He's not in the denominator. This guy's going to infinity, which, by the way, is a little bit bigger than 1, which means that this series, n factorial over 100 to the n, diverges. And that's all she wrote on that one. So that's a look at the ratio test. It's on record, so you can go over it again. I know I talk kind of quick to make these short. The concepts we cover are pretty involved. The last one back here, you don't have to worry about. It's got the same deal, except for this is what they do. They take the nth root of every term. Okay, so a real quick look at this. If I ran the root test, look what it's good for. It's good for nth powers. So if I do it on this guy, we take the limit as n goes to infinity. It's been a while since I've done a root test, but I figure I might as well round it out here. You're going to take the nth root of the absolute value of this term, which is n squared plus 1 all over 2n squared plus 1 to the nth power, without even thinking what those terms look like. You're just basically going, I'm going to run this test, and this test is telling me I can cancel nth root with nth power. This is really good if you ever see the nth power of the terms. And so let's see, we've got lim, n goes to infinity, and what we've got, that's absolute value, is the absolute value of n squared plus 1 over 2n squared plus 1. And we're supposed to take that guy's limit. And that guy's limit, look at, as n goes to infinity, is 1/2. So what? Well, here's the story. If it's less than 1, converge. Greater than 1, diverge. This guy's less than 1. That implies the series converges. So quick look at the root test in case you see that and you need to do it. I don't know why I put that in there. It just rounds things out. And that's it for the recordings as far as 11.6 are concerned. Now you got to go after those problems and do what you can, okay? I'll see you in the next one.